Hello, this is Mr. Craig, and this is the day before the AP exam 2022. Thought I'd find a nice little titration problem and work it out and just have you chill and watch the video. Hope you learned something. All right, so the first question, or the first part of the question says, in an aqueous solution, ammonia reacts as represented above. So up here's our reaction. In a 0.18 molar solution of ammonia, NH3, at 25 degrees, the hydroxide ion concentration, and again, whenever they're giving you hydrogen or hydroxide ion concentration, it is at equilibrium. They're not going to say that's what we're starting with. It is at equilibrium. Same thing with a pH. If they're giving you a pH or a pOH, it's at equilibrium. And answering the following, assume the temperature is constant at 25 degrees and that the volumes are additive. So we know that the volumes are going to be additive because this is a titration problem. So A says, write the equilibrium constant expression for the reaction represented above. We have our reactants on this side. We have our products over here. We also have water. So make sure that you're aware that water's in the picture here. So when we come and look, okay, so I kind of did everything small here. So here's part A, the equilibrium expression. Remember, we have a base. So it's Kb because we have hydroxide. Do not ever write Ka and hydroxide here. We want to make sure we get that easy point. All right. Part B says determine the pH of the 0.018 molar concentration of the ammonia. Well, the great news is they told us the concentration of the hydroxide ion. So find out what the pOH is and then find the pH. So that's what I did over here. Again, I did a lot more extra work than what was needed, but I wanted to show you how I arrived at this. So this is part B, not necessary for you to show all of this work. But again, we started off with no ammonium or any hydroxide. Again, that concentration that was given to us is at equilibrium. Therefore, that is the value for X. Therefore, later on, when we calculate the Kb, we must subtract that from our initial concentration. So always be thinking about what steps are going to be coming in the future here. So we know our pH equation is 14 minus the pOH, or pH plus pOH equals 14. So to find the pH, take 14 minus the log of the negative log of the hydroxide concentration, which is equal to the concentration that they gave us. So the pOH, we don't care about what the pOH is, but the pH is 10.75. And I put a note on here. Make sure that you have 2 decimal points or places for pH and pOH. So it's not about sig figs there. While we're here on part C, it's asking you to determine the Kb or the equilibrium constant. So again, do not include water. We know that the ammonium is the same concentration as the hydroxide because of this ice chart that I drew up here, that we don't have any ammonium or hydroxide initially. At equilibrium, we have our 5.6 times 10 to the negative 4. Since we know our concentration at equilibrium, and we know that we started with ammonia at 0.018, take that and the difference of those two, and that gives me my concentration of the ammonia at equilibrium. So that's what that value is there. Plug it in. Don't forget to square it. And our Kb is equal to 1.8 times 10 to the negative 5. So A, B, and C, everybody should be able to get that without any major issues. Okay. All right, part D, we just did C. Determine the percent ionization of the ammonia. So when we talk about percent ionization, it's all about how much did we start with. Okay, so I have percent ionization. How much did we start with, and how much do we have at equilibrium? Now, this is not on your equation sheet, but again, you've got to process and think about, okay, what does that percent ionization mean? Well, we started off with just ammonia. I know that ammonia is not an ion, but when it reacts with water, it produces these 2 ions. And all we really care about is the hydroxide. Why do we care about it? Because that's what they gave us. So we're going to focus on the percent ionization, which would be the same for the ammonium as well. So at equilibrium, I know I have 5.6 times 10 to the negative 4. My initial concentration was given in the problem. Divide that, multiply it times 100, that gives me 3.1 repeating as my percent of ionization, or percent ionization. All right, part E, we start our titration portion here. This is mainly the reason why you came here. And again, I like this question because there's concepts embedded in the parts here. So it says in part E, in an experiment, 20 milliliter sample of the ammonia, 0.018 molar, was placed into a flask and titrated to the equivalence point. What does equivalence point mean? Moles of acid equal moles of base. So in this case here, the ammonia is the base. How do we know that? Because we're asked to find a Kb value. And the HCl is your acid. So again, we're always going to titrate a strong with a weak or a strong with a strong. No weak with weak. Not in here, not on this exam. I says determine the volume of the 0.012 molar HCl that was added to reach the equivalence point. So again, we want to find out how many moles of HCl we need to add, and then we can work backward and find out the volume. So we know our volume, we know our molarity for the base, we know our molarity for the hydrochloric. So this is a great time to pull out the MaVa equals MbVb equation. We're actually solving for the volume for the acid, which in this case is 30 milliliters. That's all you need to do. You don't need to work and find out how much or what else you need to do. It's all about moles of acid equal moles of base. So we need 30 milliliters of the acid to reach the equivalence point. Okay. Double I, get this smaller. Double I asks, determine the pH of the solution in the flask after a total of 15 milliliters of the strong acid was added. Whoa, 15 is half of what we just found. We know that there's a special thing that occurs or that we can find real quickly if we know the halfway point at the equivalence. And again, the halfway point or the half equivalence point deals with how much of the strong you're adding. So if we hit the equivalence point at 30 milliliters for our strong acid, half of that is 15. Okay, so in this case here, let me blow this up a little bit. So at the half equivalence point, we know for acids that the pH is equal to the pKa. Well, we can also work backward and say that the pKb is equal to the pOH. However, keep in mind that when we look at pOH and pH, those are two different critters. Okay, so some of you might not be comfortable with doing that with bases, but this is true. The pOH is equal to the pKb for bases. Don't forget that as the pH gets more basic, that number gets bigger. So we would start at, say, for a strong acid, it starts real close to 0 or around 1. And then when it gets really basic, it's around 14. Now that's on the pH side. But you flip the scale when you go and talk about pOH. So if it's a very basic solution, it could be 0 or very close to 1. So got to remember that the pOH is going to be the negative log of what the concentration is. So I've got my pOH at 4.75. So it's asking for the pH, so we need to take 14 minus the pOH. That gives me a pH of 9.26. And keep in mind, when we're thinking about our titration curve, let me see if I can draw on here while you guys are looking at that. Let's see here, take a little sidebar. Okay, so if I have a little titration, I may have to, oh, good, it is working. So keep in mind that when we look at, I'm going to blow this up a little bit. Sorry, kind of winging it here as I make the video. So if we start with a weak base, oh shoot. If we start with a weak base, we're going to gradually drop. Now this is a terrible curve. Let me redraw that. I can do that. Apologize. There we go. All right, so when we look at our curve, it'll pop up here. we'll pretend that this is a pH of 7. So pH of 7 right here, or 7.0. Remember that at the half equivalence point, okay, at the half equivalence point, let's let that pop up, give it a second, there we go, that with the POH, okay, so this is a pH mark here, so this is pH, so we would need to find out what the heck is that POH. So when you find that point, that we're going to say, okay, there's our pH value, the 9.26 that we just found here, that 9.26 value, we want to find out and convert that to what is the POH. Because once we find out what the POH is, the POH is going to be equal to the pKb. So that really can help expedite a process here. Now, what we've all been talking about, for the most part, is if I start with a weak acid and we go the opposite direction like this, let the red line pop up here. So then we say, okay, at the half equivalence point here, I'm sorry, that should say half right there. So at the half equivalence point, then we know that the pH is equal to the pKa. Okay, so, sorry, let me let that edit. Okay, so the half equivalence point on the top and the bottom can give us a K value. So we have to keep that in mind. That will help speed things up. Now, you can, if you need to, you don't like that process, you are more than welcome to do this process that we did in class. I hate to say it, it might take a minute or two more, but if you're not comfortable or you don't remember, or maybe something happens and you just blank out and you can't remember that the pH is equal to the pKa or that the POH is equal to pKb, then this process is always here. So what you want to do is take the volume of your base or whatever your weak is and find out how many moles. Take the volume of your strong, in this case it's strong acid, find out how many moles you have. Remember that early in the question it said that the volumes are additive, so 20 plus 15 equals 35. Convert that to liters, that gives you your molarity. Come to your ice chart and say, okay, well, whichever one is smaller goes to 0. We're not at the equivalence point because, again, we need to have the same number of moles, and we know that at the equivalence point it's 30 mils of HCl to equal the number of moles. So knowing that I have less hydrogen, the hydrogen will go to 0. It will not fully react with all the ammonia. We will have some ammonia left over. And if you like using the Henderson-Hasselbalch equation or not, you can use the Ka or the Kb equation, plug that in to find out what your pH is. But notice that these two values are the same here. So in that case, let me double check here. I meant to highlight that. So this pH here is the same as the pH up there. Okay, so again, when we're finding out what a pH is, this process will never let you down, but College Board did say, okay, well, you know what the equivalence point is, 30 mils, and they were saying, okay, what happens if you add 15 mils of your strong acid? It's like a gift from the chemistry gods. You gotta accept it. All right, and then the last part here, triple I says determine the pH of the solution in a flask after 40 milliliters of the 0.012 molar HCl has been added. So recall that we said that you need 30 mils or 30 milliliters of the strong acid to reach the equivalence point. At that point, the moles of the hydrogen ions are equal to the moles of the ammonia, NH3, and at that point, all of the ammonia is gone. It's gone. You might say to yourself, well, it's at equilibrium. Yeah, okay. There might be one that comes back or two, but essentially it is gone. So I put some notes on here. At the equivalence point, let me blow this up. At the equivalence point, or when the equivalence point occurs, when all the ammonia, or NH3, has reacted with the hydrochloric acid, which is your strong, the equivalence point occurred after 30 milliliters of the hydrochloric was added. 40 milliliters of hydrochloric minus 30 milliliters of hydrochloric, the amount needed to reach the equivalence point, means that we have 10 milliliters of excess hydrochloric acid. That is the thing that is determining the pH. So what we need to do is take our 10 mils, find out how many moles we have, and then we're going to make sure that we find out what our total volume, so 20 plus 40, last time I checked was 60. So then take your moles divided by your total volume, and that gives me 0.002 molar of the hydrochloric. Take the negative log, gives me a pH of 2.7. So again, the process of, and the thing that I would say, these last bullet points here are the only ones you need to show to get the full credit. But again, if you love doing this, nothing wrong with that, because again, here we still have our total volume of 60 mils. We have 20 plus 40. Again, we needed 30 mils of hydrochloric. It's not the same volume. It's the same number of moles that we need to reach the equivalence point. So when I add those together, I get my moles of hydrogen. Again, the 0.036 should be the same as what we had up here. Again, mole-wise. And then to find the molarities, this is what I get for my molarity in my ice chart. Whichever value is smaller, so I'm going to use up all the ammonia. It goes to 0, and I'm going to have excess hydrochloric. So what that means is, looking at this ice chart, I don't care about the ammonium. That is not what's going to tell me the pH. If I have a strong acid or strong base remaining at the end, that is what I'm going to focus on. Take the negative log of that. That'll give me my pH. All right, that looks like that's all I'm going to say, and that was a little over 15 minutes. Rock and roll.